Cool. Can you see the slides?
Yes.
Yes.
Good. All right. Yeah. So you probably know the work now. So I'm going to present the work. Robot asks for help on strategy alignment for large language model planners. So my name is Alan. I'm a PhD student from Princeton and also a student researcher at Google DeepMind. So this work was done starting earlier this year until my summer internship. And yeah, this work will be presented at the conference on robot learning this year later. Okay. So just some background. I work on robotics. So in robotics, there has been increasing adoption of machine learning in the whole pipeline. So typically we have, like, let's say image inputs. We have cameras on the robot that takes the image as input. And we have some machine learning, let's say, model that directly maps the input to some action output. So let's say how to move the fingers to rotate Rubik's Cube, or how to, like, which direction to go for the autonomous cars. However, the safety is still like difficult to achieve with machine learning based systems. So how can we provide formal assurances on such systems? The main technical challenge is generalization. How can we provide guarantees on safety and performance beyond our finite training data sets? So this is just an example of the challenge of generalization, where I think this is a Tesla car driving down the highway with autonomous driving running right now. But then the perception system is mistaking the moon on the horizon as a yellow traffic light. So the car will actually constantly braking. So this is a particular challenge with generalization to these kind of difficult or corner scenarios that's beyond the training data set. So yeah, for today's talk, I will focus on language instructor robots. So generalization of language instructor robots. So just a bit more background on using language models for robot planning. So there has been a growing body of work of applying language model for robot plannings. So we can use these language model to generate long horizon plans. That because we can leverage the prior knowledge and the rich semantic context in these models. The language model can perform abstract reasoning to some degree, and it's able to generate robot code that can directly run on the robot, actually. But still, we still have this challenge of generalization. So how can we ensure reliability of language instructor robots, where we want the generalization to diverse instructions and environments? The two main challenges here I want to highlight. The first one is, as we probably know, the language models are often hallucinate. So it will confidently generate like outputs that are wrong, but with high confidence. Another challenge that's sort of unique to the human aspect is that when we instruct a robot to do something, there's often a high degree of ambiguity in language instructions. So language is inherently ambiguous sometimes. So we don't want the robot to act arbitrarily when there's ambiguity, but instead it should ask for human for clarification. So we have this kind of a motivating example in the paper where the instruction is to place the ball in the microwave. There happens to be two balls in this case, in this scenario. One is metal and one is plastic. And it's possible if the language model or the robot does not ask for clarification, it may arbitrarily, let's say, choose to pick up the metal ball and put it in the microwave. And that can be a safety hazard. Turn down the volume a little bit. Yeah. So this is what we able to do eventually, which is the robot will ask for human clarification, and the human provides the feedback. And then finally, the robot executes the action. So yeah, we want the robot to know when they don't know. So the robot should know when it's unsure between options and ask for human help or human clarification. So in previous work, these previous work either does not seek clarifications from the human, or they require very extensive prompting to like elicit these kind of asking for help behavior from the robots. And they cannot ensure that seeking help actually results in a desired level of task success either. So in our work, we formalize our goal as what we call uncertainty alignment, which has two components. So the first component is what we call calibrated confidence. The robot should ensure a statistically guaranteed level of success by seeking sufficient help. So ask for help will improve the success. So we want the robot to ask for enough help such that it will reach, let's say, 90% of success. But meanwhile, we don't want the robot to always ask for help. I think we want to say, if the robot is sure, in this case, it should go execute the action without asking for human help. So we call this minimal help to minimize the overall amount of help that robot needs. And you can think of this as the optimization problem, where we want to minimize the overall amount of help that robot needs, subject to the constraint of calibrated confidence. So in this work, we have two key ingredients to achieve this goal. The first one is planning as multiple choice Q&A, MCQA. Doing this kind of MCQA format will give us a relatively unbiased uncertainty from the model. And the second component is using conformal prediction to formally quantify the uncertainty, which I'll touch upon later. So I'll start with the first key idea of the approach, which is planning as MCQA. So how that works is, let's say we have this instruction for the language model, for the robots, place the ball in the microwave. We'll first ask it to generate possible plans. So we ask, what are some possible steps for the ball? And then we ask the model to generate, let's say, A, B, C, D, these 4 different possible plans in the context. In practice, we do some few-shot prompting. So we give some examples of this in the prompts. So then the language model will follow the same format and generate, let's say, A, B, C, D, these options. And then we ask the model, the same model, to choose from these options that it just generated. So we ask which one is correct, and then we can get the log likelihoods that's being assigned to these options from the model. So this whole setup, which we call multiple choice Q&A, reduces the next step prediction in planning to next token prediction. So we only look at the log likelihood for the next token prediction, which is relatively calibrated from the language models. So this helps eliminate the length bias associated with like scoring sentences with, let's say, a perplexity score. So normally, when you score the likelihoods for like longer sentences, the model will tend to assign a lower probability to longer sentences. So that's a bias that we don't want. But by doing this MCQA setup, we can reduce it to a next token prediction by predicting a single token, which is unbiased in this case.
Sorry, can I just ask a quick question here? So,
sure.
Why only 4 choices? Why not more?
We could do more. We could definitely do more. I guess there's a couple. I mean, first of all, this is a design choice we have. We typically find 4 is enough to cover the possible ambiguous scenarios in our settings. But you're right. I think there are other settings you might need more than 4. We can definitely do that. But also, I will say, the data set that we use to train these large language models, let's say these SAT questions, they usually have like 4 or 5 choices. So we try to put the number of choices sort of in the same distribution of what we usually see in these training data sets used for training the language model.
Okay.
Yeah.
Can I ask a question for this?
Sure.
For this, do you need to assume that the generated 4 choices actually include the optimal action?
Yes. Yeah, that's a good question. I didn't put it here. We actually have to include another option, like option E, which is an option not listed here.
I see.
We have to include that option such that we cover all possibilities, right? Because for conformal prediction, we need the ground truth. So sometimes the ground truth is not covered by these 4 generated ones. So we do have to include the 5th one here.
Sorry, can you mention again what is the 5th twice that you include?
Oh, we include, like, it's we use an option not listed here. So it's a different option. You can also use, let's say, none of the above. None of the above options. Yeah. Or we say like an option not listed here, which we will use. Yeah.
Oh, thank you.
So can I ask one more question?
Sure. Yeah.
Yeah, so clearly it has a higher likelihood for C here, right?
Yes.
Can it not? So it is still like understanding the difference between a metal bowl and a plastic bowl.
Yeah, possibly. Yeah.
Yeah. Okay.
So I guess in this case, yeah, we could just choose the highest option, which is C. But then if the situation changes a little bit or we perturbs a little bit, this can be different. So
Okay.
I think in a lot of cases, we still want to be more conservative.
Got it. And sorry, is it understanding the difference? Could it be because it's like some kind of a reinforcement learning or something? Okay. Yeah, thank you.
Okay. All right. Yeah, moving on. The next main component of the approach is using conformal prediction. I'll just quickly go over here. I will get to the details later on. So yeah, we do formal uncertainty quantification using conformal prediction. This allows us to provide statistical guarantees on task completion. It's also precise, so the prediction set will be small, which helps achieve the minimal amount of human help that we need. Conformal prediction does not assume knowledge of the input distribution. It's so lightweight and easy to use. And we can just use it as a wrapper around the foundation models with growing capability these days. We don't have to, we can just take an off-shelf the model and then apply conformal prediction on top of it. Okay, so next I'll go over the problem formulation. So in every episode, the robot is placed in an environment. You can think of an environment as a robot in front of a kitchen counter with some objects, for example. And we'll provide a language instruction. Let's say, place the bowl in the microwave, please. For the goal. The goal here is actually to pick up the plastic bowl in the microwave. That's what human really wants. But this language instruction can be ambiguous. So this goal may not be completely observable through the language instruction. So collectively, we call a scenario consists of the environment, the language instruction, and the goal together. And we assume there's an unknown distribution D over the scenarios. So this is what the planning and the human interaction looks like at the end. So we first generate these environment context. So it describes the environment. So let's say there's a microwave, a landfill bin, a recycling bin, and a compost bin. So this is some environment context for the robot. And then the robot has observations. So let's say the robot sees there's a metal bowl and a plastic bowl on the counter. And then we do the MCQA setup where we first ask the model to generate these possible next steps. Let's say these are 4 different possible steps. Collectively, we call the instruction plus the environment description, and these generated plans as the context, XT. And then we reduce the problem to MCQA, and the set of labels now are A, B, C, D, E, the 5 possible choices. This is the class of labels. And then with conformal prediction, we can generate a prediction set, C of XT, which is a subset of these possible labels. And then we use the confidences of the language model to check whether we should include the option in the prediction set or not. And then we look at the prediction set size, and we trigger for help whenever the prediction set has more than one option. So it's non-singleton. So let's say here the prediction set has two options. Then we trigger for human help. And let's say Then the language model generate a question based on the prediction set. Let's say, which one do you mean? Do you mean the plastic ball or the metal ball? And then the human provides the feedback in this case. And then we have some low-level action module that converts the chosen option to an action for the robot to execute.
Sorry, can I ask one question? So this
Sure.
the language model that generates the follow-up questions for clarification.
Yep.
It's the same model as the one that generated the multiple choice question answers?
Yeah, we just use the same model. We just ask it to, we do some few-shot prompting to, let's say, give some examples of prediction sets and some expected question, and it will learn to generate the clarification question based on the prediction set.
Okay, so it's same language model, but they are being prompted differently for two different tests.
Yeah, for they're prompted differently. Yes.
Yeah, okay.
Yeah. It's a pretty. I mean, we assumed it's always the correct reaction, and in practice, we find it that it works well. Like, there's no error from the language model for this part.
Okay.
Yeah.
Right,
can I ask a question? So, did you fine tune the
Sure.
model on this task, or did you just
No.
utilize it in context learning?
Just in context, and there's no fine tuning in our paper. No.
I see. Thanks.
Yeah. I mean, for a baseline, we tried to do fine tuning, but it didn't work well. Maybe we just didn't spend enough time on it. But yeah, we couldn't get the fine tuning to work well for these tasks. Yeah.
Was there any reason for that? Like, why the fine tuning didn't work out?
So we use the OpenAI models, like a much smaller model. Like, we didn't actually try to fine tune, let's say, the Palm models from Google, which we use here. We try to fine tune the OpenAI models, and maybe it's just the capabilities of those models are just too weak right now. I mean, maybe with the new like GPT 3.5 model now, you can fine tune, it might work. But yeah, we try to fine tune it. The capabilities are like, it wasn't able to generalize to new questions that we provide.
Yeah. Can I ask, how many contexts did you provide or demonstration did
For
you
fine tuning,
provide? For
Oh,
in-context learning.
I would say 4 or 5. Yeah, maybe 5. I think. Yeah.
Thanks.
Yeah. So yeah, I mean, so the main in-context learning part is to learn to generate these 4 different options. So we do give like 5 examples in the prompt with the context and the reasonable next plans, right? We want to teach the robot these are some possible ambiguities, such that it will learn to generate like similar options.
Yeah, makes sense. Thank you.
Yeah, I have the examples in the paper. Cool. All right. So in the context of the problem formulation I just talked about, here are like concretely what the calibrated confidence and the minimal help means. So for calibrated confidence, the robot's policy succeeds with user-specified probability 1 minus epsilon over new scenarios sampled from the Arnold distribution. And the minimal help is the policy minimizes the number of options presented to human on average across the new environments that we sample from the distribution. Cool. So I want to make a slight detour here to talk about predictor guarantees from frequentist and versus the Bayesian point of view. So when I talk about probabilities in this talk, I'm talking about the frequentist view. So if I run my robots, let's say 1 million scenarios from this Arnold distribution, I want to see 1 minus epsilon percentage of successes. And this Arnold distribution, the distribution is unknown, and we assume we have some RID samples for calibration. So this is different from Bayesian probabilities, for example, based on Gaussian processes or Bayesian ensembles. There, the probabilities are inherently tied to prior, and then the probabilities are more like a belief instead of an actual, percentage of successes that will happen, or the actual probabilities the robot will succeed. And I do think when we deploy the robots in large scale in the future, we want a frequentized interpretation for formal assurances in robotics. We want to say, I'm 99.9% sure the robot will work, which means 1 out of 1,000 times, only one time that the robot will fail. So that's kind of an interpretation that we want. Cool. All right, next I'll go deep into the conformal prediction part, which I think you guys might already be familiar with. But I'll just give you a quick background on the work. So yeah, in this work, we are in the classification setting. So for each input, we will predict a set of labels. So X is the context, the input to the language model. Cx is the prediction set, which is a subset of the possible labels. So yeah, this is an example from the gentle introduction to conformal prediction. We apply conformal prediction to image classification setting, and we can generate these prediction sets that covers the true label, which is the fox squirrel here. Then the prediction set will contain the likely classes for the image. So in our context, we have because we designed the setup into an MECQA setup, we reduce the prediction into next token prediction. And then the class labels here are A, B, C, D, E, the 5 options. And then the prediction set is a subset of these 5 labels. So conformal prediction provides calibrated coverage. So the true label will be contained within prediction sets, let's say 1 minus epsilon. To be able to do this, we can use softmax scores for each option provided from like supervised learning models, such as language models. So let's say this predictor f hat x belongs to a number between 0 and 1 for k different options. So we often interpret these as probabilities. So one way to achieve this calibrated coverage is to use this simple algorithm, which is to rank the options according to f hat, and then construct a set such that the cumulative score exceeds 1 minus epsilon. So this is a simple way to do it. But however, this doesn't work in practice, which I will show later, because these models can be miscalibrated. So the model can be very confident about one particular option, and then the prediction set can be too optimistic, for example, and only contain that label, but miss the true label. So what conformal prediction does is that it will give us this calibrated coverage instead. We soon have some pre-trained model, let's say a language model, and then we have some calibration data sets. Some RID samples from the distribution, we have the corresponding inputs and outputs for the model. So this uncertainty estimate I've had here, we don't make much assumption on this. That could be miscalibrated. And then this on the distribution from the data set sample form is also unknown. With conformal prediction, we can have the model outputs prediction set, and we can achieve a statistically guaranteed coverage. So for the first step of conformal prediction, yeah, we define the non-conformity scores. I'll just go over this very quickly. I guess you guys are familiar with this. So the SI is 1 minus the score is into the true label, the true clock. So the score is 5 when the softmax output of the true is wrong, when the model is very wrong. And then we define Q hat as roughly the 1 minus epsilon quantile, the empirical quantile of the non-conformity scores from the calibration data set, S1 to Sn. And then for a new test point, X test, we can create a prediction data set by including the options with high enough softmax output, include the options with scores higher than 1 minus Q hat here. And then we can achieve what we call marginal coverage. So the probability of at test time, the true label at test time in the prediction set will be bounded between 1 minus epsilon and 1 minus epsilon plus a small correction. So if we do the simple set algorithm, that kind of algorithm does not satisfy the marginal coverage because the model can be miscalibrated. But there's one note here, which is the probability here from conformal prediction is over randomness in both the calibration data set and the future test inputs. So this means this only holds if we in expectation over sampling the calibration data set. So it's very likely if we unlucky, we sample a calibration data set that doesn't satisfy this. So in practice, in our paper, we use instead the data set conditional coverage. So here, the probability here, you can see it's conditioning on a particular calibration data set S. So that's why it's called a data set conditional coverage. So the guarantee will say with probability 1 minus delta over sampling of a calibration data set, we have this coverage. And this calibration is conducted with a slightly different threshold, which we call epsilon hat. That's based on the original epsilon, the delta, and the number of calibration samples we have.
Sorry, one question. With this data set conditional coverage, you don't have an upper bound on the probability anymore?
On top of the head, I don't think so. I don't think we have an upper bound anymore, but usually we don't care about the upper bound, really. We just want the lower bound anyway. So in our case, it was okay. Yeah.
Okay. And sorry, what was this epsilon hat one more time, if you don't mind?
Yeah. So because we want to use a data set conditional coverage, essentially we are being a little bit more conservative than before, such that even though the calibration data set might be a little bit worse than we expected, we can still achieve this coverage. So this epsilon hat, the adjusted threshold will be slightly smaller, I think, such that, it will be slightly larger, such that I will include a little bit more options in the prediction set. So that I can still achieve this. Yeah.
This is the epsilon that goes into the relation for quantile? This
epsilon hat? Yes, this is epsilon hat that goes to the quantile. Yeah.
Okay.
Yeah. So it's usually the original epsilon plus a small offset. Yeah.
Okay. Thanks.
But the guarantee is still for 1 minus epsilon.
Okay. Thanks.
Yeah. Cool. So yeah, conformal prediction also gives the guarantee that if f hat is accurate, achieves minimal average prediction set size. So we can achieve minimal prediction set size with conformal prediction. So here we apply conformal prediction in our setup, and we start with a single step setting. So here the robot only plan one step for the whole episode. So we collect the data set S, which is a data set of contexts with true labels, with scenarios sampled from the unknown distribution. We perform calibration with conformal prediction. And at test time, given a new context, we output the prediction set. And if the prediction set has only one option, the robot will execute the plan. Otherwise, the robot will present the set to human, and the human will choose the correct one if there is one in the set, or it will stop the robot in this case. So this is the whole human help setup with conformal prediction together. So what the human help does is that originally conformal prediction gave us the coverage guarantee, which is the prediction set will contain the correct plan with probability 1 minus epsilon. With human help, whenever the prediction set is non-singleton, so has more than one option, we convert the coverage guarantee into the task completion guarantee, which says the robot will complete the task with probability 1 minus epsilon, which is what we really want. This is the guarantee that we care about. And this is a simple proof in the paper that I think it's really nice, where we just combine the human help aspect with the conformal prediction to achieve the task level guarantee.
And here, completing the task means that completing the task successfully, right? That's
yes, yeah. We do assume that. So we do assume that low-level action works every time. So as long as the robot chooses the correct action to do, we assume the low-level action is correct. So it will be executed correctly, and then the task will be complete.
okay.
So here, I guess you have to make an assumption that your task the horizon of your task is only one. But if you task involves multiple steps, you have to accumulate the error probability over the horizon.
Yeah. So, we do extend our like a single step setting to a multi-step setting in our paper. We do have this multi-step planning case in our paper, and we are able to give the same 1 minus epsilon guarantee for multi-step setting. So 1 minus epsilon, the robot will complete the whole multi-step setting correctly. For
the multi-step, do you assume that the horizon is fixed or flexible?
We do assume it's fixed. I guess so in our paper we use the fixed horizon, but I don't think we have to make that assumption. I think we can actually make a variable for different scenarios. Yeah.
You'd be a little bit tricky if you allow like flexible horizon, right? So I guess how you extend from single step to multi-step is actually by this union bound. You just divide this epsilon by a fixed.
We actually don't do that. We do something different. Yeah, I know typically people do this union bound thing. We actually do a calibration on the episode level, where we look at, let's say, the worst step in the episode and use that to calibrate it.
I see.
Yeah, it's a little bit different from the typical union bound approach.
I see. Thanks.
Yeah, I don't have the details here, but yeah, the downside is that. So I think in the typical union bound approach, you can use individual steps for calibration, but here we have to use episodes for calibration. So the N, which is the number of data set size, is the number of episodes we use. It's not the number of steps that we use.
Yeah,
so we do need more data to calibrate.
And I guess if you take consider the fourth step or over the whole episode, another thing I can imagine is that your policy might be a little bit conservative because you have to consider like the worst case across the whole episode.
Yeah, I do think that's one of the drawbacks that we find, but I think we haven't thought about much beyond that, but it'll be interesting to think about, like, can we be less conservative? Can we do like a non-worst case calibration for the sequence?
Yeah. So another remark. So you set the objective function as to minimize the average prediction set size, which is like very reasonable and widely used in the conformal prediction community. And I guess another like alternative maybe you consider like the number of prediction size whose size just go beyond more than one.
Yes. Yeah.
Right.
Yes. Ideally, that's what we want, actually. But conformal prediction doesn't give us that kind of guarantee. And yeah, in the paper, we chose to say we want to minimize the average prediction size because the conformal prediction like naturally gave us this kind of a benefit. But yeah, in practice, we do want to maximize the number of singleton sets, right? Yeah, there could be a way to optimize the prediction such that we can maximize the number of singleton set size. Sorry, number of singleton sets, such that we can minimize the actual number of human help. Yeah, but that requires a different process, I think.
Thank you.
Thanks. Yeah, these
So,
are
I think I missed part of it. With this multi-step planning, you have different x's. X is the input to this conformal prediction where you had cx.
Yeah.
That come one after another, right?
Yes, we will generate a prediction set at
For every
step.
x. Okay.
Yeah. And the x is different at each step, but the x will depend on the previous step.
And then you are assuming that all these x's are IID.
The steps are not IID because the context for the next step depends on what happens in the previous step. So they are not IID. The episode you can think of as IIDs. The scenarios are IIDs. Yeah.
Right, they are not IID, they are not even exchangeable, right? It's because
No, they're not. No.
okay, they are exactly. Okay, and then does that influence so this coverage guarantees of the conformal predictors? It depends on the data to be exchangeable, right?
Yes, but because we are lifting the data on the sequence level sequences, we just on the episode level they are exchangeable. They are IID. We're not doing. Yeah, the guarantee that we get at the end is say 90% of the time, 90% of the episodes will succeed. It's not 90% of the steps will succeed.
Okay.
Does that make sense? Yeah.
Okay, yeah.
Yeah. So we effectively treat a single data point in the data set now is a sequence, is not a single step.
Okay. Oh, I see. Okay.
And the episodes are IID, you can think of, but the steps within the episode are definitely not IID.
Okay, and your data points are the entire episode, not the steps.
Yes.
Okay. No,
Yeah.
Okay.
Yeah.
Okay.
Yeah.
All right. Thanks.
Yep. Thank you. All right. Yeah. Next, I will show some experiment results. Yeah, we run the setup on a simulation setup on the top left, and three other hardware, real hardware examples. So these are just some qualitative results. Here we're using mobile manipulators. This is a bimanual setup, and then we also have a tabletop. Here there's a multi-step setting where the planning involves multiple steps. I'll introduce the baselines. So the first one is simple set, what I already talked about, which is to rank the options according to the predictor f hats, and then construct a prediction set such that the accumulated score will exceed 1 minus epsilon. There's also the ensemble set. So with ensemble set, we're using an ensemble-based method where we randomize the prompt for the language model. Because we randomize the prompt, we get different answers from the model. And then we can look at the empirical frequency of, let's say, option A being chosen. And we use that frequency instead of the log likelihood from the model as the score for the option. And then we rank them and then do the simple set again, basically. Another baseline is prompt set, which we directly ask the language model to output prediction sets. using prompting. But naturally, this doesn't work well because there's no calibration. We're just giving some examples of the prediction sets in the prompt, and ask language model to directly generate the set. Next one is binary, which is to ask a language model to output a binary indicator of uncertainty. So ask it whether it's certain or uncertain. So this is typically what people use in planning with large language models, is to use such a very heuristic setup and directly ask a language model to output a single token for certainty. And lastly, just to give some background for comparison, we also have a no help baseline, which is to always execute the highest score option without generating a set or without any human help. Is there any question on the baselines? I can stop here. Yeah. Okay. So yeah, all the experiments use the PaLM-2L language model at Google, which is the biggest model that Google has.
Sorry, just a question here. So
yeah.
You actually mentioned this simple set, which you just construct a set by according to the cumulative CDF. And
yeah,
the downside for that is that if the model is not calibrated, then the simple set doesn't make sense. So in this sense, have you ever thought about or tried to calibrate or confidence calibrate the model first and then construct the simple set? Say, for example, using temperature scaling.
Yes, we tried that. Actually, yeah, in the paper we didn't include the results, but what we found empirically is if we do temperature scaling first and then apply simple set, the set is much bigger than conformal prediction set.
I see. Oh.
I'm not sure if you ever have this kind of observation. Like I don't have a good intuition for this, but we did spend a lot of time on this using temperature scaling and then apply simple sets. But then we found the set is actually very big.
I see.
Which actually is bad for us. Like it triggers a lot of help, basically.
I see. Thanks. Thanks.
Yeah. All right. Yeah. I'll go into the individual experiments in a bit more details. So the first one is the simulation tabletop rearrangement. Here, the environments include 3 different bowls and 3 different blocks with different colors. And the task is to move a certain number of objects to a location. Let's say move the green block in the green bowl, or move 2 blocks to the left of the yellow bowl, for example. So the ambiguities here of the language instruction can be, let's say, we have 3 different categories. One is attribute. So for example, instead of saying move the bowl, we may say move the receptacle. This is the numeric ambiguities. So let's say the human says move a few blocks, but maybe the human wants exactly 2 blocks or 3 blocks. There's also can be a spatial ambiguity. So let's say move next to something, move the block next to the yellow block. But maybe human wants a precise placement to the left, to the right, in the front, or at the back. So we kind of purposely construct such ambiguities to showcase the difference between our work and the other baselines. So in experiments, we found that because we have this calibrated coverage with conformal prediction, and it comes with a guarantee, our work no achieves the target success rate consistently. So the y-axis is the deviation from the target level, 1 minus epsilon. So the lower is better. And we compared different baselines in the 3 different kinds of ambiguity settings.
So can I ask a question? What is the epsilon here?
Epsilon is the error rate.
No, I mean, what is the exact number that you used here?
here is 0.15. Yeah, so we choose a fixed one.
0.15.
So yeah, so the target success rate is 0.85.
I see. Because it's not the lower the better, right? So because the ideal case is that your empirical rate is basically exact the level of your desired level.
Right. So here
'Cause-
we're showing the absolute difference, right? We show the deviation.
Sorry.
We look at the difference. Yeah, we're not looking at, let's say, the
I see.
difference. We're
Sorry.
looking at the deviation.
Yes.
Yeah.
So one other
So
question.
there's no negative values here. Yeah.
What was the size of the calibration set here?
Here we use 400. N is 400. Yeah.
So roughly speaking, all these probabilities are above the upper bound. That was 1 minus epsilon plus 1 over n plus 1. But you said that the upper bound is not really interesting here.
Sorry. Yeah. Here, this is the deviation. So it's the absolute difference. It's not the actual value minus 1 minus epsilon. It's the absolute value of that.
Oh, okay. So it can be below.
Yeah.
Also. Okay.
Yeah. So the deviation is always positive. Yeah. Yeah. We could have showed the actual difference, so which can be negative, but just for the visualization of the paper, we choose to show the absolute difference, the absolute error instead. I will say using the dataset conditional coverage sometimes can be a little bit more conservative than using the marginal coverage. Using the marginal coverage in practice, we find that sometimes we will miss the target level. Like we can be lower than 1 minus epsilon, very, very, very easily.
Yeah, sure. There's this distribution, right?
Yeah, but using the dataset conditional coverage, we never go below 1 minus epsilon. But sometimes we can be a little bit more conservative.
Okay.
Yeah, but I think that's good for robotics. Although that does mean that, let's say in the spatial setting, like no has the same deviation as, let's say, the ensemble set, or in the numeric setting, it has the same deviation from the simple set, because we're being a little bit more conservative. So the
Right.
deviation can be a little bit larger than using marginal coverage.
Right.
Okay, cool. Okay, then here I'm plotting the whole curve of x-axis is the prediction set size, and the y-axis is the task success rate. And we get this curve by changing the epsilon. So we can choose a range of epsilon from for higher epsilon to lower epsilon. So with lower epsilon, with smaller epsilon, we're asking for a higher target success rate. But that also means that the prediction set will be bigger, so human intervenes more. But yeah, when we plot the full curve with different methods, and we tend to find that our methods achieve higher success rate with fewer amount of help than needed. The binary and the no help are not, sorry, the two baseline that's not shown here because they don't give a prediction set. They only give a binary, just output one answer, and the no help does not involve a prediction set.
Sorry, is like the horizontal axis, is it the average prediction set size?
Yeah, the average prediction set size.
Okay.
Yeah. So average over the test sample.
Right.
So you will notice something about the ensemble set. So if you see the gray line, it's pretty short, but it's doing better than the other two at the lower region. The reason that is ensemble set has some issue because we are using a finite number of prompts. sometimes even we try like 20 different prompts for the same data, the correct answer is never chosen. Then the probability for the correct action is 0 in that case. So that means we can make the prediction set really big, but then the true answer is never included. So that's why we cannot achieve a high success rate, like beyond a certain threshold. That's why the line stopped there. But yeah, I think it'd be interesting to think about if there's a way to improve that, and then maybe the ensemble probability can be a better probability, a better heuristic to use than to curing the likelihood of flaw for the model. All right. Yeah, next we have the multi-step setting in the tabletop rearrangement setting. So here we have the human help rate on both the step level and the episode level, and then we can show that our method achieves achieve the same level of tasks with fewer help per step and compared to synthesis. So this is what it looks like for the tabletop setting. We basically ask the robot to store the objects on the table to a blue plate and a green plate based on the human preferences. So we generally simulate a human that likes healthy food and dislike unhealthy food. But we only give some examples in a prompt. So we don't always include the preference for the existing objects on the table. So in some cases, the language model need to guess, and sometimes it can be the model can be not sure about a particular object. So then we want the language model to ask for human. Yeah, here it triggered help for the mustard, but it didn't trigger help for the egg and the lettuce. Cool. And then lastly, I want to talk about the mobile manipulation setting. Here we have some other interesting ambiguities. For example, one that based on winograd schemas. So here, the example is there is an apple and a bottle of water on the counter. It is rotten. Can you dispose of it? So here, the pronoun it can be ambiguous, whether it refers to the apple or the bottle of water. But we do say it is rotten. So ideally, the language model should figure out because it's rotten, it should be the apple, not the bottled water. So we do find that a lot of these cases, the language model is able to differentiate between these two and execute the actions without the human help. But sometimes it can be more ambiguous. We also introduce some other instructions that can potentially have unsafe actions, such as involving putting the bowl in the microwave. And again, yeah, we are able to show that our methods achieve the target success level, which is 0.5 here, A5 here. Human specifies, let's say, 0.85 the target success level, and the no achieves the planned success rate, 0.875, A7. And then the human help rate is lower, triggers a fewer amount of help. We also tried this with 2 other language models. One thing to notice is that one thing worth mentioning is we tried this on the GPT 3.5 model from OpenAI, and we find that the GPT model has an interesting bias towards option C and option D in the multiple choice. So it's much more biased in the PaLM models. So you can see that for the GPT model to achieve the same level of task success, it uses much higher amount of help because of this human bias. But then because conformal prediction give us the guarantee, we can still achieve the user-specified 1 minus epsilon target success level pretty precisely. And yeah, the conformal prediction in this case will just compensate for the degraded language model performance by triggering more human help. Yeah, I want to end with some future work and the conclusions. So right now, for the whole task completion guarantee, we assume that there's no errors in the vision language model perception and also the low-level action policy. So can we think of ways to incorporate this in the conformal prediction? And we are focusing on, I have some ongoing work that looks at conformal prediction with perception. And can we say, given a number of, let's say, observations, given a number of images, can we make sure the prediction is correct with high probability? There's also active preference learning. So can we generate open-ended queries that maximally reduce uncertainty about human preferences? This one is relevant to Shore's question earlier. So in the paper, we mostly use the metric of the average prediction set size because it's something natural to have from conformal prediction. But we can think of, can we modify CP to optimize the different kind of metrics for human help, such as the intervention rate. Yeah, and then we also find ensembles as an interesting and potentially very powerful way to get the uncertainty from the language models. So we want to further explore ensembles for quantification of uncertainty with CP. Okay, so yeah, just as a conclusion, yeah, in this work, we propose the goal of uncertainty alignment, which has the two components, the calibrated confidence, reaching the user-specified task success level, and also to minimize the overall amount of help that human needs. With conformal prediction, we build this no-no framework that provides a lightweight wrapper around large language model planners. And we hope there can be future steps towards, uncertainty quantification and formal assurances for language instructed robots. And yeah, this is all we have. And I can take more questions if there's any.
Well, thank you, Alan, so much. Wonderful work. Great presentation. I personally learned a lot. Thank you.
Yeah. Thanks, everyone. Yeah. Yeah.
Thank you.
I mean, I can take any other questions if there's anything, but we already talked about that, I guess.
Yeah, and just some remark. It's not. So I think that fine-tuning the model to actually optimize according to the human preference might be interesting. This actually reminds me, I don't know whether you know that or not, there's a paper called this learning-based conformal prediction. So that paper actually trains the model.
Yeah. Yeah, there's a differentiable CP framework.
Yes.
Not sure, yeah. Learning optimal conformal classifiers, I think.
Yes. And the reason why I mentioned, ask why whether you did fine-tuning or not, is I guess if you do in-context learning for every prompt, it might be a little bit costly, right? Because the context might be really long. And if you actually do fine-tuning,
right. Yeah, in our work, we use the fixed prompt for every scenario. But yeah, we had to design the prompt pretty carefully
and also,
to improve the performance.
And also, I guess you have to input both the context and the query to the model for every query.
Sorry, what do you mean? I don't quite get the point.
So what I mean is that when you do a text generation, you have to at every time you have to input both the context, your demonstrations, and also the new query. And if you do fine tuning, you only need to input the query.
I see. Yeah, that I agree. Yeah, I see. Yeah.
Yeah, and I was a little bit surprised that actually the fine tuning didn't work out. That might be interesting to see.
We have a discussion in the appendix in the paper. Yeah, I might try again. It didn't work out for us last time.
Yeah, thanks.
Yeah, thank you. Yeah, these are really great questions. Have you tried the differentiable setup before? Just curious.
Not for my project. I read their paper, and I do think like they have some very interesting applications where that work can be applied to your setting, which is minimize the ambiguity set directly. Because if I recall like correctly, they actually considered this setting. They minimize the number of set whose set is go beyond 1.
I see. Yeah, I don't remember exactly, but I do remember that their experiments had a number of different kind of metrics to optimize. I think.
Yes.
They tried the different things. Yeah. So I'm mostly working on this perception part right now, using CP for perception, and we're trying to use this differentiable setting to optimize speed because. Sorry.
What kind of task are you using for the perceptron?
Is
it object detection?
Yeah, or it can be, let's say, in a simulation, I ask a question like how many chairs in the room.
Oh, I see. I see.
The agent or the robot has to move around in the room to get new observation. Yeah.
I see.
Yeah, or object detection, like challenging object detections. We have to change the view orientation, for example.
But makes sense.
Yeah. I think the interesting part of perception is that right now we're trying to include like predictions from different models. Let's say vision language model or language model together. There's an issue of how can we figure out let's say the weights when we combine the predictions. And right now I'm trying to use the differentiable setting to optimize these kind of weights when we combine the scores from the. Yeah, let's say somehow we want to combine the predictions from the different models. And I want to find the optimal weights such that the prediction set is, let's say, minimized.
Actually, I had a work related to this topic before. So if you're interested, we can talk after this. So basically,
I see.
I guess we're considering about the same one. Like if we have multiple components, how should we like aggregate those components in the most appropriate way so that we can minimize or optimize some objective function?
I see. So you have different components in your pipeline. You have end-to-end guarantees?
Yes.
I see. Okay, that's really cool. Yeah, that's something I definitely want to think about, especially when we want to combine like prediction combine a perception with planning or with a low-level action together.
Yes.
Really useful. Yeah. Maybe I'll look at the work. Maybe I can find a different time we can find different time to set.
Yeah, that would be great.
Yeah, that'd be great. Yeah.
But all right, I don't have any other questions. Thank you again, Alan. This was a wonderful presentation.
Yeah. Bye.
All right.
Thank you.
Thank you, guys.
Great. Yeah. Bye.
Bye.